Hello friends, I am Amir Nizami, and today we are going to derive the governing equations for the Euler-Bernoulli beam using the direct method. So we have the three methods as already I described. So this is the direct method we are going to use for that. So we know that the governing equation of the Euler-Bernoulli beam is very well known to everyone. That is EI del 4W by dx to the power 4 equals to qx. So how it comes? So So, undergraduates, we have studied that if there is any beam which is loaded with the distributed loads, that is Q of x, okay, and let's say it is supported, suppose. So we take a strip, okay, anywhere, and very small strip. We just take it out. Let's say the length of that is dx, and we will just zoom it up, and we will make it somehow like that, okay. So this is the dx length, okay, and what the load is, that is the q of x load, and we have the reactions corresponding to that. So let us say v of x we have, and on this edge at a distance dx length, what we have from the terrestrial expansion, it is vx plus dvx by dx into dx, okay. And what would be the moment here at both the ends? So we have the moments, let's say moment at this edge is m of x, and moment at this edge would be m of x plus d of mx by dx into dx at the distance dx from this edge, okay. So now let us first find the equilibrium conditions along the vertical directions. Let us say in that y direction, if we say this is the y direction, so let us sum up. So we can assume that in the vertical direction it is positive, so summation of fy should be equals to 0. Now all the upward directions we are considering positive, so let us just sum up all the forces. So v of x is in the upward direction, that would be positive. Q of x is acting downwards, so minus of q of x. To make it the load, equivalent load, point load, it would be q of x into d of x. Yes, this distance would be multiplied, so d of x, and then this force would be what? This is downward direction, so it is minus of vx minus dv of x by dx into dx, okay. That should always sum up would be equals to 0, then it would be in equilibrium. Yeah, to maintain the equilibrium this is required, okay. So now this capital plus vx and this minus vx would get cancelled, okay, and then what is remaining? If you take both sides on the right side of that, so let us do it. So what we can write, dv of x by dx, okay, and multiplied by dx. So this dx and this dx, let us simplify. On the right side it would be minus of q of x, okay. So this is what we are getting, dvx by dx equals to minus of qx, okay. Now we have this relation with the shear force. V is what? The shear force. Yeah, we can see it is a shear force. Shear force having the relation with the external distributed load. So shear force with external distributed load. We have this relation. Okay. So let us say this is the equation 1. Now the second, let us have the moment. So sum of all the moments. Second equilibrium is moment about the point A. So let us say this is a point A. At this point A we are finding. So moment about point A. So summation of that, sum of all the moments about A should be 0. And let us take anti-clockwise as positive. Okay. So now just see what are the moments acting at this edge. So this moment is acting as clockwise direction, so that would be minus m of x, Okay, and the next, this moment is acting anti-clockwise, so that should be plus m of x plus dmx by dx into dx, and also some forces would give the moment. So this shear force is passing through the same point, so there would be no moment because that the distance would be 0 from there. So 0 moments would be provided by this Vx, and this Qx will provide, because this Qx is a distributed, it should be made as a equivalent concentrated load. So it would be Qx into dx. The load would be equivalent to Qx into dx. Okay, so it would be acting at the center, and this distance from this point would be Qx dx into dx by 2. Okay, so that is that moment would give in the clockwise direction moment, so minus Qx into dx into dx by 2. Okay, then because this is giving the clockwise direction, so minus we have taken about this point. Okay, and then which one remaining? Remaining this. So this is the Vx plus dvx by dx into dx, and the distance is how much from this point to this point is dx. Okay, so plus v of x into dx distance, and then that should also be minus. This should be minus also. It is giving clockwise direction, minus dvx by dx into dx into dx. Okay, so that's what we have. Okay, okay, fine. Now that all should be equals to 0. Okay, so this now what cancelled, minus mx plus mx get cancelled. Okay, hence we know this length already we have told that this is very, very small. Dx is small or very small. So if you multiply small with the another small number, it would be very, very small. Yeah, very, very small. So this can be neglected. So if it is there, so now this dx, this dx, so it is very small. Okay, so it would make a very small quantity, very, very small, very, very small quantity. So we will neglect it. We will tell it is assumed to be 0. Okay, then what? This dx, this dx. Okay, so this dx is very, very small, very, very small. We neglect it. It is also 0. So what are remaining now? Let us see this dmx by dx. So this is remaining and this is remaining. Okay, write it, dm of x by dx into dx, and then minus v of x into dx equals to 0. Dx would get common, it will come out. What is the remaining function? dmx by dx equals to v of x. So it gives the relation of moment and shear forces. So moment and shear force relations. Okay, so rate of change, that is the bending moment, is the shear force. So it is equation 2. Okay, so the first equation we got this relation for the shear force and the external loading. This is the bending moment and the shear force. Now what we know, if the beam get deflected, okay, so let us say if the beam is there, so definitely due to the loads it would get deflect. Yeah, so what is this deflection? This deflected part is what? This is the w of x. Yes, this is what w naught of x, because it's a function of x only, as it will approach so 0, and then finally it will reach to 0 here, and in between somewhere it would be the maximum displacement. So that is all the displacement that is occurring is a function of x. Yeah, as x we are changing, the displacement values are changing. That is the transverse displacement. Okay, so this curve what I am plotting here, what is this? This is the w naught of x curve. Yeah, that is the deflected shape curve. Okay, now if we take the slope here, okay, if we take the slope at any point, how we take the slope? We make a tangent to that. Okay, and how we measure the tangent of the slope? With the x-axis. Okay, so that is the theta. What is that? That theta is the del WF naught of x by del x. Yes, that is that. Or it is clockwise, it would be minus sign. That is the slope. Okay. So the tangent to this point gives the slope. And what is the curvature? We know. What is curvature? Curvature is what? Rate of change of slope. So d theta by dx. That is the curvature. Okay. That is the curvature because it's bending. So if it is bent, so what's the curvature if you want to find? So curvature would be the rate of change of slope d theta by dx. And if you want d by dx, theta is what? We have already found minus del w naught of x by del x. Okay, so it would be minus d2 w naught of x by dx square. That is the curvature. Yes. And what we have the relationship with the bending moment and curvature? M beta EI. So M by EI equal minus d2 w naught of x by dx square. So then the bending moment would be minus EI d2 w naught of x by dx square. Yes, this is the bending moment and curvature relation. Yeah, so relation between bending moment and curvature. Okay, so this is the relation 3, equation 3. Okay, now coming back, what is the shear force having the relation with the bending moment? Now let's do V of x. Shear force is having the relation with the bending moment, that is d of mx by dx. Yes, and d by dx of mx is what? Mx is just written here in the equation 3. So substituting equation 3, what? Minus EI d2 w naught by dx square minus EI d2 w naught of x by dx square. Okay, so minus of EI d3 w naught of x by dx cube. So the relation of the shear force with the transverse displacement is the third order derivative. So minus EI times d3w by dx cube. Okay, that is, let's say, equation 4. Now coming back, what's the relation? Now the first one is dvx by dx equals to minus of qx. So now the shear force is having the relation as d of v of x by dx equals to minus of q of x. Okay, what we do? D by dx of what? Minus EI d3w naught of x by dx cube. Okay, equal minus q of x. If you take the derivative, what would be there? Minus minus taking outside from both, plus EI d4w naught of x by dx to the power 4 equals to q of x. That is the governing equation. What we got finally? What we got? EI d4 w naught x by dx to the power 4 equals to q of x. Finally, we got this governing equation of the beam using the direct method. Okay, so in next lecture, inshallah, I will try to take with the principle of virtual work. Okay, thank you.